All right, I'm back. We got total pressure equal to 1.8. My pen back here. Total pressure equal to 1.859 atmospheres. So that's the answer to A. Let's go over here and do B. Calculate the partial pressure of N2. So again, we could do a separate one way to do it. We could do a PV equals nRT and just use the moles of N2 to get it that way. Or we could do the pressure of N2 is going to be equal to the pressure total multiplied by the mole fraction for N2. And I'm going to do it that way. So this is going to be equal to this value here should be 5.485 ATM.
Lunch is here. Come and get it. And then the center faculty room.
5.485 ATM multiplied by the mole fraction. So the moles of nitrogen were 0.4128. And my total moles are 1.2, whatever I put in for 1.22. And that's going to be equal to 1.859 atmospheres. Very common thing. A lot of times in the multiple choice section, they'll give you total pressure and just moles or grams of each, and you have to go about this process. So we got B. We saw that there are two different ways. Either way is good. Okay. C says that if you made a little pinhole in this, okay, and you have nitrogen and you have helium, and you allow it to exist over time, which gas would there be a greater percentage of? Now helium, since helium's smaller, it's faster than N2. Okay, it diffuses faster, it effuses faster, and it's got a greater speed. We see that helium has a mass of 4 and nitrogen has a mass of 28, so that's a faster one. In this case, we're talking about effusion, which relates to escaping from a hole in a room if you are a gas. So in this case, nitrogen will be left because less escapes because it has a larger molar mass at 288 Kelvin. So indicate that they're at the same temperature, because this is really going to say that they have the same kinetic energy. Remember, kinetic energy is only related to temperature. Moving on to problem 3. So for A and B, what I would like you to do is see kinetics vodcast for work. It should be located here. If you go down and say see kinetic vodcast on final, I do work through this problem. The rate order is 1 here, it's 1 here. The overall rate law will be rate equals K I minus to the first, CLO minus to the first. First order for each, second order overall. So you calculate the value for K. I believe it's like 611 or something like that. Liters, moles second. K, if you think about this, is kind of analogous to Y equals mx plus B. Y is kind of analogous to the rate. The slope of this is m. And what affects Y is x. And these are the concentrations of the reactants. So it's a similar situation. If this is squared, it'll be parabolic. Currently it's linear. What is the oxidation number on chlorine before and chlorine after? So before, in ClO minus 1, chlorine, X minus 2 for the oxygen equals 1. Chlorine must be 1. So before, it must be plus 1. And after, we all know, they simply just gave that to us, it's minus 1. Okay? And based on this, chlorine was reduced, so it is the ox agent. Based on your answer to C, is the atomic radius of chlorine larger or smaller? Well, it's both chlorine atoms. They're over here on the right, so they have a pretty small radius. But chlorine minus 1 is larger because it has 2 more electrons than chlorine plus 1. Very simple response. Alright guys, that's the end of part A. Going on to part B. This is the non-calculator section. You do not have to do this. This is our standard magnesium example that they're going to give to you every time. Chlorine gas, Cl2,0, is bubbled into a solution of potassium bromide. Alkali metals are separated in water. In this case, chlorine is going to go down. Bromine is going to go up in charge. So bromine is going to be oxidized, and chlorine is going to be reduced to Cl minus. Potassium is our spectator ion, and we're going to have to balance by putting a 2 there and put a 2 there. Please rewrite this over, not showing the spectators, just to make sure you get maximum points. Okay, chlorine is 0 before, and the 2 chlorines are minus after. Solution of nitric acid is a strong acid because it's on your list, and another way of remembering it is it's got NO3, which is always soluble, is added to a 0.1 molar solution of sodium carbonate, Na plus 1, CO3, 2 minus. I see ions, so I'm going to do my connecting and cancel. I also saw ions above, so I did my connecting and canceling. Got my arrow. Na is going to go with NO3, and it's going to be separated for 2 reasons. There's an alkali metal, and it's with nitrate. In this case, we're going to make a weak acid, carbonic acid, but this always breaks up into H2O and CO2. So I'm going to have H2O here, and I'm going to have CO2 here. NO3 is a spectator, and Na is a spectator. And I need to balance by putting a 2 here. Write the rate law expression that is second order for carbonic acid. I meant nitric acid. And 0 order for sodium carbonate. So rate equals K. Nitric acid is basically reduces to H plus, and I said it's second order, and it's 0 order for sodium carbonate, so I don't need to show it. Okay, so this means that sodium carbonate is in the fast step because only the slow step affects the reaction, and if only the slow step affects the reaction, only the slow step is in the rate law. Okay, last one. Calcium oxide is dropped in water. It's solid, so it's just calcium oxide, solid, it's dropped in water. Now, whether you have a metal oxide or a simple metal, if it's an alkali metal or an alkali earth metal, the first thing you need to do is write that hydroxide. Hydroxide is going to be produced, and the other thing is calcium 2 plus. Now this is a strong base, so it's going to be separated in water. There it is. We do produce OH, so it's a basic solution. pH will be greater than 7. OH minus means it is basic. Alright guys, stop there, and I'll see you a little bit later. Take care.